Hi everyone, let me introduce who we are. We are Eva Mohedano's team and we are Diego Tascón, Darío Cortizo and me, Luisa Fleta. Our project name is Synthetic Satellite Image Generation using GANs, and our project seeks training a conditional GAN to obtain realistic satellite image from masks representing the building's areas. This is the content of our presentation, and I'll start with the motivation. Conditional GANs offer many applications for generated tailored image. Using them with satellite image sounded attractive and also has a practical use case. What is the practical use case? Annotating image, especially aerial ones, is a hard and very time-consuming task. So, a conditional GAN training to generated images from forget mask can help increase the size of the aerial dataset. And this is the motivation, increase the size of the aerial dataset. Now I'll explain the model. Next one. The implementation, what we use are pix-to-pix architecture. A general idea is that pix-to-pix consists in two neural networks that solve different tasks. The first is the generated network that will be in charge of learning to generate a satellite image from a mask. The generator that the model uses is unit ResNet block, and there is a skip connection between the ResNet blocks. Our generator is fed with a mask in train and inference time. Then, once trained, outputs are similar images to an aerial photograph, with building in the location where the labels were in the input mask. You can see here the mask in the left side and the generated image in the right side. The second task of this architecture is the discriminator network. The discriminator network will be in charge of learning to identify whether the image has been generated by the generating network or it is an image of the original datasets. In the pix-to-pix architecture, the discriminator is implemented with a patch GAN. That is a fully convolutional network designed to classify patches of an input image as real or fake, allowing to capture more details from the image. Our discriminator is fed by two images because the discriminator acts as a loss. Now I will explain the losses of the model. The model has two losses, one for the generator, another for the discriminator. The generator loss combines two losses. One is the adversarial loss generated by the discriminator, predicting whether the generated image seems real or fake, considering the mask provided, is the LDOS. And the second is the content loss. This loss regularizes the generator model to output images that are good translation of the source image. The content loss does that comparing the generated image with the ground truth through a L1 loss. Finally, we have a lambda because we can give more or less weight to a content loss. The discriminator loss is a composition of two losses again. In the first loss, when the model encourages the discriminator to learn that a ground truth image is real. How do we do that? Calculating the MCE between the mask plus real image and the value true. In the second one, the MCE between the mask plus fake image and the value false. And this is the discriminator loss. Now I will explain the dataset. The dataset we use is in real aerial imaging labeling. This dataset has 118 images and the corresponding building mask. And we have 5 towns or landscapes. They are Austin, Chicago, Kipsan, Tyrol, and Vienna. Also say that the image have 5,000 by 5,000 pixels and the format is TIFF. And finally, the satellite image have 3 channels and the mask have 1 channel. The framework that we used was Python, and the computational resource were mainly Google Colab and Google Drive. And we used Docker for occasional local tasks and Google Cloud for very long training. For the milestone, we have 3 points. The first one, we could train the model with the Picket implementation and the selected dataset. Several runs were done to find a nice combination of hyperparameters. The second one, we generated a pre-processing dataset that improved the speed, and we generated a new dataset by data augmentation, and the quality of the image improved too. And in the third one, we substitute the content loss by BGG loss, and some aspect of the generated image improved, but we didn't test it with the intermediate convolutional layers of the BBG. And finally, we didn't substitute the ResNet block of the unit with the already pre-training ResNet block. About the project plan, until the delivery of the critical review, we worked on choosing dataset model implementation, and when we had decided this, we studied the code and we worked on finding the best hyperparameters for our model. After the critical review, we work on improved results and different strategies and comparing the results. It should be noted that since the beginning of January, we have been building the project report. And now Diego will continue.
Thank you, Luisa. Good evening, everyone. I will explain now how we started the project and which were the strategies we developed to improve our results. So we picked already implemented model for Pix2Pix and trained it with our dataset was more or less straightforward. We played around with the different hyperparameters until we found a combination that gave us some decent results, as you can see in the slide. One of the issues we had at the beginning was performance, because the model resizes any input image and any input mask into 286. And since the original images were 5,000 per 5,000, so in every epoch and every iteration, all this resizing plus some transforms were executed, and this slowed down the training. So we decided to create a new dataset, resizing the original images and masks into the expected size, plus making all the transformations and save that as tensors into disk. We modified the model so that it read them from disk, and the data loader still performed the random crops and random flips, and they gave us a boost in our train times. Moreover, we also decided to store in memory the already read tensors, so that from the second epoch of our trainings, no access to disk was performed. Even if the first results were, let's say, decent, they lacked from detail. So one of the things we thought was increasing the pixel resolution. In the original dataset, every pixel represented 30 centimeters of land or of landscape. And when resizing that to 286 per 286, that pixel resolution changed to more than 5 meters per pixel. So we thought that increasing that resolution could let the model learn more details from the photographs. So we created 2 new datasets, one for, let's say, a mid-resolution dataset by splitting into 4 equally sized tiles every mask and an image. We applied the same downsize and transforms to save them to disk. And so this way, that allow us to augment the data we could provide to our model at the cost of having 4 more times, or training 4 times longer than previously. So we trained our model with this mid-resolution dataset, and we obtained this. We had color problems, saturation, and we tackled this problem with a different strategy. I will explain later. So our second new dataset, we split it every image and mask into 25 equally sized tiles, and also downsized and applied the same transforms. And that resulted in a pixel resolution of about 1 meter per pixel, which we thought that could help even more the model to learn. The downside was obviously the huge training time needed to accomplish this. And in fact, we weren't successful. We couldn't complete a whole training with the same conditions as the other trainings. Anyway, we tried with fewer epochs, and the result was surprisingly good for us. Hence, anyway, that the results you can see here are come from a combination of different strategies. I will explain now. One of these strategies was changing the normalization layers from the generator. The original one used batch normalization, and we saw that some research teams had found that substituting batch normalization by instance norm helped them to get better quality in their images. In batch normalization, the whole batch in every iteration is taken into account to make the normalization, whereas with instance, individual normalization is done image by image. And so it worked, as you can see on your right. Color problems disappeared, although some checkerboard effects were produced. Another strategy we tried to improve the quality of our images was changing the regularization. As Luisa has explained, the generator has 2 losses, one coming from the discriminator, classifying the images whether they are real or fake, and another one, which is a content loss that compares the generated image with the ground truth image. The BGG loss has a similar approach to this latter one. It uses a BGG19 network pre-trained on ImageNet. And in this network, we are feeding both a generated image and a ground truth image. And we extract the features coming from the last convolutional layer. And we calculate a mean average error within them. So we implemented this into our model by giving a new lambda hyperparameter so that we could play with different weights to see what gave the best results. And we found that substituting completely the original content loss with this new BGG loss which gave us the best perceptual results, although it had a cost in almost doubling the train time. Here you can see a comparison between, on the left, what gave the original network, what was the result when substituting the content loss with the BGG loss, and on your right, what happened when combining both at the same time.
Well, hi guys, and I'm gonna finish off the strategies, and then I'll talk about results, conclusions, and next steps. As our last strategy, we use a data filtering. I mean, it was when early on we realized our data set was pretty much divided into two different types of landscapes. We had rural landscapes and we had urban landscapes. The masks coming from the rural landscapes were pretty low in pixel density, which pretty much means that some of them were black images, and we were feeding these black images into the model, and we basically were holding down or putting an obstacle into how the model was mapping this input mask into output objects. Basically, the model was hallucinating all the shapes, and then we have a lot of blurriness on the images, and also an overexposure of green-like colors in all the images. So we decided to, if you move on, Diego, to the next slide, we decided to develop or to filter out these images using a pixel ratio, which is basically computing the amount of white pixels over the total number of pixels of the image, and filter out these masks. And on the left, you see examples of these generated images with yet all these almost black masks. And the best one to see this or exemplify this is the one on the top right corner. You see all this blurriness on the middle. It's because the mask is pretty much black and the model doesn't know what that shape means, so it's just hallucinating this organic weird blurriness. And on the right, when filtering out these rural landscapes and also on remaining or narrowing down the scope into the cities, pretty much, we have a more stable color control. We basically erase all this blurriness, and all the greenish or green-like overexposure that we saw on the previous images, it went away a bit, or at least we were able to tone it down. So now, talking a bit about results, the first question is, how did we evaluate our results? We basically had two different paths or strategies. The first one is qualitatively, by a visual inspection of the generated images. And the second one, quantitatively, using mainly two metrics, the PSNR and the FID. The PSNR is a relation of peak signal to noise ratio, and it's calculating or computing the L2 or MSC distance between the generated image and the real image, and then converting this into a log scale. And the FID is a bit more sophisticated in the sense that we are feeding both the generated and the real image into an Inception V3 architecture, which is pre-trained in ImageNet. And then the predictions coming from this network are compared and a distance is computed. And if the distance is equal to 0, it means that the images are pretty much the same, or it's a perfect similarity. And the further away they are, or the bigger the distance is, the more different these images are. It turned out that, if you go to the next slide, it turned out that visual inspection is the most reliable one of these three strategies. PSNR in particular was pretty erratic. I mean, it was not reliable at all. Sometimes it was low when the image quality, at least from our visual standpoint, was good. The PSNR, the higher the better, supposedly, but it was pretty erratic, so we didn't really rely on it. And the FID was more in line with our perceptions. Sometimes it slipped off, and we were not completely agree upon what the distance was suggesting, but in general was much more reliable than the PSNR. So now we're just briefly touching the two main environments that we use throughout the project. Collab, both of them have their pros and cons. Collab was pretty fast, but it was at some point a nightmare when you have to train for a long time, because I mean, the kernel shuts down and you have to frequently save a lot of checkpoints. And to be honest, it is an overall not good experience. So we decided to set up a virtual environment in the Google Cloud platform, which we expected that would be faster, but this is probably something you can fix up if you just get a bigger graphic card, dedicated card. But in general, it was pretty stable. We were able to throw very long training, and the overall experience was much better. Now I present here a summary table, basically compressing our principal runs. The first one is the original implementation, the off-the-shelf implementation, which we call low resolution. We also show the FID for all of them. Our best runs were the third one, the high resolution. Unfortunately, we lost the checkpoints and we couldn't compute the FID. The next good one, or the next best one, was the mid resolution, the fourth one, which, as you can see, the FID is lower than the first one. And this, with using instant normalization on L1, we were capable of eliminating the saturation, these color saturation problems that Darío mentioned before. And the last one, using instance and VGG, regularizing the generator loss, was actually, the images were crisper. There were a little bit more of high detailing in some part of the images, but we were not agree with the FID here. I mean, this is definitely not the best run. So that's the reason I mentioned that the FID is not always a reliable metric. So the next one is, this visually summarizes our journey. Let's say on the left, we have one of the first images that we generated from the off-the-shelf implementation. And we went from that to the image on the right, which is obviously a zoom-in image. But in here, the model is capable of capturing high details like the cap, the tree caps. It's painting rooftops, it's painting buildings, it's painting the roads, it's painting grass. I mean, we were pretty happy about the result. We thought at some point that we couldn't get this level of detail, and increasing the resolution of the pixels and changing instant normalization for batch normalization for instant normalization and running for 3 epochs, I think it was, we were capable of getting to this point.
Okay, you have 1 minute, okay, so please.
Okay, so there's I'll go through the conclusions rapidly. We went from training an off-the-shelf pixel-to-pixel implementation, and this was at the beginning quite unstable, but we were capable of getting some results. But we were not convinced about these images, so we implemented some ideas, as we've already mentioned, which were increasing the pixel resolution by cropping the images, filtering the input mask when they were very low in pixel density, normalizing, changing batch for instance normalization, regularizing the generator loss by means of the VGG. And then 2 comments on the metrics. This is not something that we solved. I mean, it's something we have to dig deeper. And the infrastructure, if we had probably more hardware resources at our hands, we could have probably parallelized more experiments and run more strategies and maybe come up with a better solution. But for that, we have some ideas here in next steps that I just enumerate fastly. We could have chosen other implementation. We did try a different strategy with the learning rate scheduler, but it didn't work. We could augment our mask, our input mask, fine-tune the pixel ratio, and filter out these masks in a better fashion. Then improve the upscaling layer from the unit architecture, because this gave us problems with checkerboard effect that we kind of solved using increasing resolution. Maybe embedding an extra layer of information on the mask, like labels or a splash of color, and then transfer learning, maybe using some pre-trained architecture. So this is pretty much it, guys. I hope you've enjoyed it, and if you have any question, we'll be glad to answer. Thanks.